So I welcome all of you to today's class, and today we are dealing with shear stresses in beams, lecture 10. Now we deal with the introduction, shear formula, and then shear stress distribution in standard sections, and then some work examples. Now, stresses produced in the beam are generally due to shear and bending. Bending stresses were considered in our previous lecture, right? Now, a shear force in a beam at any cross-section sets up shear stresses on transverse sections, the magnitude of which varies across the section. So we noted last time that when we come to bending stresses, whenever we have bending moment, the resulting stresses are called bending stresses. And now again, anytime we have shear stresses or shear force, the resulting stresses are called shear stresses. Kezia, I thought your hand was up. Okay, let me continue. Now, in the analysis, it is assumed that the shear stress is uniform across the width and does not affect the distribution of bending stress. That is the reasonable assumption for this. As every shear stress is accompanied by an equal and complementary shear stress. If you remember strength 1, we dealt with complementary shear stress. Shear stress on transverse planes has complementary shear stress on longitudinal or horizontal planes parallel to the neutral axis. Calculation of shear stress are important, although shear deformations are relatively small. The bending stresses are more dominating in majority of the cases. So what we are saying is that even though shear stresses, their magnitude is small compared to bending stresses, it is extremely important to calculate their values and know their magnitude as based on whatever member you are designing. And so, once again, anytime you have bending moment, you have accompanying bending stresses. And if you have shear force, you have accompanying shear stresses. Now let's look at the shear formula. Now in derivation of bending equation, the beam is assumed to be subject to pure bending and no shear force is considered. As a result, only longitudinal stresses called bending stresses are produced in such cases. All right. Now, if a beam is loaded in a transverse direction, as in the case most common in practice, shear stresses and bending moments, both are produced. So what we are saying is that most of the time, you have bending moment alone acting. You have basically bending moment and shear force acting in the beam. And in effect, they will produce the bending stresses and shear stresses respectively. Now, shear stresses are due to shear force acting along the depth of the transverse cross-section of a beam. For equilibrium of the cross-section, complementary shear stress of equal intensity are considered in longitudinal planes parallel to the axis of the beam. Okay? Now, let us consider this. Okay? let's consider this. Let us take what you are seeing here is simply a beam, okay, supported at various parts. And so this is just like you have a beam like this, okay? You have support here, you have support here. And we have just cut a section at the top like this and remove this small part. We have removed this small part, and that's what you are seeing. So this is the surface, okay? And this is also another surface, all right? So take it as if we have section QR and section TS. The length we are considering is delta X. Okay. Now, here again, what you are seeing here is very simple. It's like we have a beam like this. We have a beam like this. And then we take a section, let's say section 1, 1 and section 2, 2. So this is what you are seeing here, okay? So we have the beam and we have just cut a section. So call this one 1 and call this section 2. And we are saying the length of this we are considering is dx. Of course, you know, small length we will say is dx like that. And that's what we have done in the past. February. Now, when we cut the section in the previous slide, okay, this is the surface we were seeing, okay? This is the total area we saw in the previous slide. Now, this one, we just want to consider a small area here, which is the shaded for a small area called dA. Now, we are looking at bending moment and shear force acting at the same time. So first of all, we are saying that at section 1, if we have moment to be M and shear force to be F, then by the time we get to section 2, it would have changed. So there will be some additional moment to the original moment. And there will be some additional shear force or shear force to the original shear force. That's why you have M plus dm. And then okay. I'm getting some message that there was some joint research team for something. Anyway, that's fine. I'll make a decision at the end of the class whether the assignment still holds or it doesn't hold. All right. So if it is M here, by the time we get to section 2, the moment would have increased by delta M, small moment. And the shear force will also have increased by a small shear force. Okay. We are saying this small area I've shaded here, that is it. Okay, so this is an elevation, the B is elevation, and this one is cross section. Okay. Now, so on the right hand side, we are saying that F, capital F plus DF, they are all shear forces at the two sections. And then moments, M plus DM, they are moments at the two sections. Then we are saying that the distance from where this section is being considered to the neutral axis. Know this line represents the neutral axis. We are calling this to be y naught. And that's what you are seeing here. Okay? Then the area of this small portion we are considering is the delta A. That is small area. And the whole area is actually the shaded portion. Now, Z or B will represent this Z you are seeing here. Okay? Or B represent the width of the beam. So this represents any shape. Okay? This one represents any shape. Okay. And so now let's proceed then. I want to clear the screen. Then we proceed. So this is what we have noted now. Now, let stress and stress plus delta stress be the bending stresses on the transverse plane as a result of a bending moment. So once again, this thing you are seeing here is a small area we are considering. So if you want to find the force on this, everybody knows that stress is what? Force over area. All right. So if that is the case, then force is what? Stress times area. And this is the stress times what? Area. So the area here is a small area, dA. Now we remember that in our previous lecture, bending stress, we know that stress is what? M over I y. Okay? So this has been substituted here and the dA. Force applied on the right end of the elemental area is giving us. So this one is the left end here. If you move to the right end, like we noted, if moment will transform to moment plus dm, then it makes sense to say that the stress will also transform to the stress times the stress. Okay? So that's what we are seeing here. Okay? So instead of the now, it is moment plus dm over I dot y. So equation 1 and 2. So 1 is for this surface. And then the equation 2 is for this surface. Is that right? And in simple terms, for equilibrium, when we sum these two forces, we should get 0. In other words, for equilibrium, the force on this face must be equal to the force on this face. Let's proceed. So remember these two equations, equation 1 and equation 2. Now, so we are saying that the net force simply means one of the force minus the other. So this one is simply equation 2 minus 1. Okay? Net force equation 2 minus 1. So this is the equation 2, and this is the equation 1. Okay. Now from here, when we expand this one, you note that we have m here, which is positive, m here, which is negative, so this will go. We have delta m over I left here times y. So we can factorize this out now. Okay. We have I as a factor here. So when we simplify, we'll get this. So this is just the force on the small element as we were considering. We have a big part, but we took a small area here, which was delta E. So if we want the total force, then integration comes in, or summation, sum all the small to get the big. So it means we have to integrate equation 3. And that's what we are seeing here. It's like summing all. Because moment usually we know. Okay, let's keep it there, equation 4. What about shear force due to the top? The shear force acts on the surface. Okay? So if we will go back a little bit, you know that the surface here, this is the surface. This is the surface. And the shear is on this surface. I see. So shear, everybody knows stress is force over area. Okay. So shear stress is also shear force over area. So if I want the shear force, is what? The shear stress times the area. And the shear stress, as we see, the area here is the Z by the D. So Z by delta X is the area. Okay. And then the shear force also comes in. So it's the same as tau. We said as Z to use Z or B. So it's B dx. Okay. All right. So let us note the equation. So this is the total force, equation 4. And the equation 5 now gives us the total shear stress, shear force, total shear force. That's what. So this is applied, and equation 4 is applied, and then equation 5 is the total shear force. Okay. Now, for equilibrium, we have to equate the two. For equilibrium, we need to equate these two equations. This one and this. So let's now make tau the subject here. So we take this one to the other side of the equation, and that becomes this one. Now, because usually moment and the I, we know it, we can take it outside of the integration. So in this case, it is like constant, and we know the rules of integration, and it doesn't affect the constant. So we take it out of the integration sign. Now we have stress y dA, or integral of y dA. So dm over dx. If you remember, when we're dealing with bending moment, we dealt with relationship between shear force, bending moment, and then load. And I said dm over dx will give you shear force. df over dx will give you small load. And again, we said if you integrate the load, you get shear force. If you integrate shear force, you get moment. These were some relationship we established right from that lecture. So this simply means that the dm over the x simply means the shear force. And then y dA, if you remember, we are representing y dA as a y bar. Okay? So if you remember, this is the first moment of area. First moment of area, if you can remember. And this one help us to get our y. So we are calling this quantity a y bar. So if that is the case, in summary, the tau is equal to F over B dot I dot A y bar. And basically, this one is the formula for shear force. And of course, from the formula given by Professor Kezia, she gave tau is equal to VQ over IB. So in this regard, the Q is the A y bar, okay? And V is our F. So in this lecture, we are using capital F to represent shear force, even though we can also use V, right? And we are using the A y bar to represent the Q. All right? Any question? Any question for clarity? If there's no question, I'll proceed. Okay, so finally, we have been able to see how this shear force formula came by. Now, I want you to take very good note of certain key things here, because you have ability to understand the formula and see how you will be able to apply this formula. In this formula, the tau or tau means the shear stress across the section. The capital F represents our shear force at the section. So the shear stress, that's what essentially we are looking for. So if you have a beam like this, maybe with series of loading, and we are asking you to determine the shear stress at maybe point C, then you find your reactions, you cut your section, and then you cut a section here between these points and look for the shear force at this section. And that is this shear force as you see it. Now, we've learned about calculation of moment of inertia, all right? So with a moment of inertia, depending on the section, either if it's a standard section, you have a formula. So you use either the integration formula or whichever. And we have learned about parallel axis theorem to be able to calculate moment of inertia of any shape. So you apply any of these principles to calculate your R. Then the B, which is actually the width of the section at the position where the tau is to be calculated. I want to illustrate this clearly, okay, using a section like this. Supposing this is the neutral axis, right? Supposing this is our beam. If let's say this is C, this is, let's say, okay, let me just take the C and bring the C down. If this is C, and I'm determining the shear stress at point C, remember this is the depth of the beam, depth of beam. If I'm determining the shear stress at C, then my B is measured along that path. So this now becomes my B. If I'm determining the shear stress here, then from here to here becomes my B. If I'm determining the shear stress here, then from here to here becomes my B. So the B is the actual width of the section at the position where shear stress is to be calculated. Okay. What about Y bar, distance of the CG of the area from the neutral axis? Again, if we have a section, let's say we have this rectangular section. Of course, we should know our neutral axis. And with the neutral axis, we have noted that this is essentially the D for rectangular section. And from here to here is D over 2. From here to here is also D over 2. Okay. And we have established that we measure Y from the neutral axis, Y, and then from here down, Y. That's what we have established in our previous lecture. So if I want to calculate, what is my Y bar? What is my Y bar? If I am to calculate the shear stress at, let's say, point C, if I draw a line here, the distance from the C to the neutral axis is my Y. I hope you get that. That is my Y. So all the area above my Y, or to the extreme point of the member, is the area I am looking for. This is your capital A. So you have to establish the center of gravity. This is rectangle, so establishing center of gravity is somewhere here. So this is CG. So from here to the neutral axis is now my y bar. I'll come again. Supposing we are finding the shear stress at D. If I draw a line here, the distance from the neutral axis to my D here is the y. The area from the y all the way to the stream part of the section is my capital A. Now, if this, like we see, this is rectangular area. So if I draw something looking for the center of gravity to be in the middle. So from the center of gravity of this area to the neutral axis is my y bar. Okay. I think that is clear enough. If I take this to be another section, this is the neutral axis. If that is the case, if I am finding the area, the shear stress at this point, then from here all the way, everything above that line is my area. And that's how you consider it. At any point, or all the area above is considered as your area in question. Okay. And then you try to find center of gravity of that area to the neutral axis, and that becomes your y bar. So the y bar is moment of area about the neutral axis. Okay. And the area of the cross section above the level at which the shear stress is being evaluated. All right. Any question? Any question? Okay. So silence means consent. So let's proceed. Now let's look at, I want to let you know that the shear formula we just look at is the general formula for any shape at all. Is the general formula for any shape at all. Now we just want to look at application to some standard sections and see whether we'll be able to get some simple formulas to use. So we want to look at standard section. So let's look at rectangular section. As you already know, our shear formula is F over I IB A Y bar. Okay. So we want to look for the parameters for this rectangular section and then substitute into this, simplify it, and see what we get. All right. So let's look at the parameters one by one. First of all, if we are looking for the B, note that we are looking for the shear stress at along EF. Okay. Shear stress at EF here. Okay. So now the distance from the neutral axis to this point is a y. So because this is rectangular section, the B at that point is equal to B, which is the width. What about A? The A of this section, the A we'll be looking for is after the Y, everything above the Y is my area. And look, if the whole of it from A to this point is D over 2, and then this one is Y. If I'm looking for this distance, It's very easy now. It's simply d over 2 minus y. Okay? And the width here, this rectangle, the width is b. So the area is simply b times what? D over 2 minus y. And then let's look for the y bar. So if this is the area, rectangle, if I cross here and also cross here, this is the center of gravity. So from the center of gravity here all the way to the neutral, this is my y bar. Okay? So what do you think? Y bar is simply the y plus half of this. So we have y plus half of the d over 2 minus y. So now that we have gotten this, we'll just substitute into the main shear formula and simplify. Any clarification required here? Okay, I forgot to let you know that the shear, so for rectangular section, the shear diagram or shear variation diagram looks like this. Okay, so you are calculating at various y's. Okay, so you look for your, so this line here represents the depth of the beam. So if you calculate the shear stress here, you mark, it's a graph, you mark. So from here, whatever shear stress value you have, from here, whatever shear stress, you keep marking. When you finish, connect all this with a smooth curve, right? And that will give you your shear diagram. Now, if you can see clearly here, you see that Q max means maximum shear. And this maximum shear is located at the neutral axis. If you remember what we did, when it comes to bending stress, the maximum bending stress was at the top extreme fiber. But when it comes to the shear stress as we are dealing with, maximum shear stress occurs at the neutral axis, irrespective of the section. So let's take note of that. So our next slide is just going to show substitution of this thing we have just calculated here to get our, okay. So let's go and do our substitution. So these were the things we're establishing there, okay? This is the main formula. We established this one. We have established this one there. We have also established our y bar, okay? And once again, we also know that our B is simply equal to the B, right? If this, what you are seeing here, if this is simplified, you get this, okay? So we are now going to take this one, put it where we have the A. We take this one and put it where we have the y bar. And then, of course, the B remains, the I and the F. So when that is done, we'll get this equation here, alpha. So I want you to write this equation down. Tau is equal to F over 2I, D squared over 4 minus Y squared. So what is the main difference now? So this equation is only applicable to rectangular section. Okay? Now, what it means is that if I want to calculate the shear stress here, all I need is my Y. If I want it here, all I need is my Y. And this make it more easy to deal with the problem. So when you have a rectangular section, you want to calculate the shear stress at various points, you use this equation alpha to deal with the problem. So here you calculate your F from your shear force diagram. Your I you can calculate from your section. you know for rectangular section, we know that D represents the depth. And then, so what is not known here is the y squared. And remember that if I'm measuring y here to be positive, y down should be negative, okay? And vice versa. Okay. So I hope you have noted the formula. Let's proceed. So we just want to do some substitution, okay? At the top edge, this is the rectangular section. At the top edge, y is equal to a d over 2, because this is d over 2. This is also d over 2 for rectangular sections. So when we substitute d over 2 into this formula, we'll get 0. So it means at the top edge, y is d over 2. Well, the shear stress at the top is 0. At the neutral axis, what is value of y? Neutral axis, y is 0. So substitute 0 into this same equation again, and we will get tau to be equal to f d squared over 8i. So here we want to simplify further and say, okay, if we decide to put the I, because this rectangular section, the I is BD cube over 12. If we substitute this into this equation, what do we get? And when we do that, we are going to get 1.5 F over BD. Okay? In other words, 3 over 2 F over BD. All right? Let's proceed. So this implies that for rectangular sections, the maximum shear stress acts at the centroid, at the neutral axis. And in fact, it's for all sections. For all sections. So at the neutral axis, this is what we established. And this is the same as 3 over 2 dot F over BD. Okay? And that's the equation beta. And we are saying that if we represent F over BD as tau average, if we call that one average tau, then what should be the final thing? We can also write maximum shear stress at 1.5 times tau average, or 3 over 2 tau average. Okay? All right. So note equation beta and gamma down, because if I give you a question and ask you to find the maximum shear stress, you don't need to do a long calculation. This one is simple. For rectangular, is equal to what? 1.5 F over BD. All right. Now that is for rectangular section. Let's look at another interesting section, an I section. So for a typical I section, in fact, this is symmetrical. This is how the shear diagram look like. This represents the depth. So here we call this the top flange. I'm giving you the label of an I section. This is the bottom flange. And this one, we call it web. The web is small t, bottom, the flange is capital T, and the thickness of the flange, top flange, is also capital T. And the overall width of the beam is the capital B. And the overall depth is the capital D. And the inner depth from the inner part of the top to the inner part of the bottom flange is a small d. And this neutral axis is passing through the middle of the small d because it's a symmetrical section. And if that is the case, this is what you have as your shear stress variation diagram. Now, because of the nature of the section, we are going to deal with this separately. We'll consider variation in the flange, and we'll also consider variation in the web separate, so that we can get our formulas easily. So this implies that when you calculate your shear stress in the flange, you plot. And then when you calculate here, you also plot, and you join this with a straight line. And this part, you plot as you are calculated. And then you join this with a smooth line. This is straight. And this is the shape for symmetrical isolation. So let's consider it one after the other. Okay. So let's deal with the flange. Once again, our formula is tau is equal to F over I B dot AY bar. This is our formula. So what are we looking for? Let's look for B. Let's look for A. And let's look for Y bar. So for this section, as I mentioned, we are looking for the stress at here, okay? This is where we want to calculate the shear stress. And the distance from the neutral axis to where we are calculating the shear stress, as we already know, is always y. And this one, we are dealing with the flange. Note, we are dealing with the flange. Okay? All right. Now, what is the B? So now, because we are in the flange, the width there is the capital B, and that becomes our B. Let's go to the area. If from here to where we are looking for the force, the stress is y, and we know that from the neutral axis all the way to the top is d over 2, then it's easy for us to find this small distance. What do you think? This small distance now is simply equal to d over 2. No, this one is capital D. Sorry, it's capital D. From here to here is capital D over 2. Okay, so this one is now D over 2 minus the Y should give us this small distance. So if you want the area, what do you think? The area above the point we are looking for is simply the D times capital D over 2 minus Y. What about Y bar? Okay. If this small distance here, okay, if we are to draw a line here to locate our CG, this to be our CG, then the distance from the CG to the neutral is the Y bar. So what do you think? It is, everybody knows that from here to here is D over 2, as we saw in the previous slide. So it's simply D over 2 plus half of what? D over 2 minus y. And this should give us the y bar. So now that we have finished, we just substitute this into the main shear formula. Any question here? Any question here? Okay. Let me attend to Isaka. Isaka. You have to unmute. If you don't unmute, when you talk, nobody will hear you. I can't hear you. Oh.
Sir, please, I don't understand.
You don't understand which one?
The whole show.
I'm sorry. I'm sorry. I cannot address your problem. I'm sorry. I'm proceeding with my class. I don't entertain those. Okay? If you don't understand the whole story, you start all over again. That's how we learn. You know, that is a phobia term. That term, when you bring it, once you bring that term, it's phobia. I won't mind you cry. Okay. Who was Zoom and how do you tell me the whole show? Victor. Yes.
Don't mind it's not don't mind.
Come again.
Don't mind, don't mind. It's not serious, don't mind.
Oh, don't, yes, I won't. I mean,
Yes, because if you go back, we are rather putting our brain back because our places, it's not easy like that.
okay.
Thank you, sir.
You're welcome. All right. So, well, I see another hand up here, Joshua. Joshua? Joshua? Hello, Joshua.
Yes, sir.
Uh-huh.
Please, I would like you to go over the Y bar.
The Y bar. Okay, that's fine.
Yes.
I'll do that. Okay, so what I'm saying is that let me try to maximize just the top pair. Okay, let me exaggerate it like this. We are saying that we are finding the thing somewhere here, so which means this whole top here is our area to be considered. So it means we need here, and we also need here. We need also from here to here. Okay. So if this my neutral has this line, for this type of section, we note that from here to here will be the capital D over 2. What then is our Y bar? We need to find center of gravity, region of this area here. And from here to my neutral axis is my Y bar. So now I have to calculate. What do you think? From here, where I'm finding my shear stress is always my Y. Okay? So if this is my Y, then how do I get from here to the middle? It's simply this distance. Half of this distance plus the Y should give me my Y bar. And as we noted, this distance here is what? Capital D over 2 minus Y. This small distance here. So it should be Y plus half of this distance. That should be able to give me my Y bar. I don't know, Joshua, whether your problem is addressed. If it's addressed, you can just say yes in the message box. Otherwise, you can raise your hand and let me know what is not right. Okay. All right. So let's proceed then. So what we are going to do now is we are just going to substitute the B, A, Y bar into our main shear formula and then just simplify it. Okay. So in the next slide, that's what we are going to do. So maybe if you can write these ones down, fine. I'm clearing the screen. Okay. Okay. So this is exactly what we did there. Okay. So there's nothing new here. We have done this. We have done this. This one has been further simplified to this. That's the only difference. We have simplified this one to this. Okay. So now Y bar now is this one. So we'll go and put this one here. This is the B. So the B will come and put it here. And this is the A. And the A will come and fix it here. Okay. And then we simplify. Okay. So now, when we do that substitution, I want to make this known that because we are dealing with a flange, I'm using tau F, meaning the shear stress in flange. Okay. Then, so after substitution, you do simplify it. And when you simplify, you get F over 2I, D square over 4 minus Y square. Okay. And note that this one is for I section, which is valid for the flange only. So if you want to calculate the shear stress within any portion of the flange, this is the formula you are going to use. So in this formula, we note that the capital D represents the overall depth of the beam or the I section. So what will be changing is the Y, the location you want to find your shear stress. So you just be changing the Y values and then voila, you are good to go. All right, so note the equation 1 down. And note that this is just for the flange only. Okay. Now let's proceed. Let's look at the web. Now, because they have different width and it's like irregular shape, that's why we try to deal with the web separately from the flange. So this one is in the web. Once again, tau is equal to F over I B dot A Y bar. This formula remains. Now, if we are dealing with the web, then from the neutral axis, any point at all. So we are saying that here, we want to find the shear stress here. So as we have learned, it means all the area above that point is a capital A. All right. So we have to look for, these are two different sections. Okay. These are two different sections. So we are dealing with the web. Okay. So the B, we are dealing with the web. So the B is equal to what? Small t, because that's the thickness of the web. area. Because we have two parts, we can have A1, we can have this to be A2, because it's kind of a complex figure. I can't find the area very easily. And then, so in this particular part, we need to be able to find A1, Y bar 1. And then we'll find A2, Y bar 2, because we have divided it into two parts. So the A1 Y bar 1, A2 Y bar 2 are components you need to find, so that finally you can find A1, AY bar to be equal to A1 Y bar 1 plus A2 Y bar 2. This is what you do if you have many parts. Okay? But as for the B here, the B is applicable to where you are actually determining the shear stress. Okay. So let's see if we'll be able to deal with this. For this I section, as we know, from the top here all the way to the middle here is capital D over 2. From the edge here to the neutral axis, this is small d over 2. Okay. So if you want to calculate for A1, A1 is this, the width of this one from here to here, and then the B is here. So if you want to know this width, then we can simply say that then is the overall D on 2. When we subtract distance from here to here, which is D over 2. If we do this, we'll be able to get this small area. Okay. So now the A1 is simply length times breadth, because it's a rectangular section. So A1 is what? D times D over 2 minus D over 2. Okay. Now again, let's look at the I think that I mixed up some things. So here we'll look for the A2, and then we'll look for the Y bar 2. So let's look at the Y bar 1 for the A1. This is rectangular section, so we can draw this and draw that. So it means that from here all the way to here is the what? Y bar 1. Okay. I think that is pretty easy. If we add D over 2 to half of this, which is D over 2 minus small d over 2, we should get the distance from here to the center of this area 1. Okay? So I'm saying that we know from the neutral axis here to the bottom part here, we know say that one will be D over 2. And then this thickness here, we have estimated it to be what? D over, capital D over 2 minus small d over 2. So half of that, D over 2 minus D over 2. Okay? So let's look at the area 2. The area 2 is here, from here to here. So first of all, this is where we are, and this is Y. So how do we get this small length? It's simply D over 2 minus the Y. That's easy. From here to here to the neutral axis is D over 2, and this is Y. So when we do that, we'll get this small height here. So the area 2 now is the small t times what? The D over 2 minus Y. That's the small t, the A2. What about Y2? Okay. The Y bar 2, when we deal with this one, center of gravity. We can measure from here all the way to here, and this is y bar 2. What do you think? Is half of this distance plus the y. Okay? So it's simply the y here plus half of this distance, which we estimated to be d over 2 minus 1. Okay. All right. So now that we've got this, we can substitute those that you have to simplify. You can go ahead and substitute into this one so that you get the a bar, y bar. Okay. Any clarification required? Any clarification required? Or everything is cool? Okay. So in the next slide, what we have done here, that's what you are going to see there. We are just going to put them together. That's all. All right. So you see that everything is here. So the only difference is that this one, part 1, okay? I think that even this one is not needed. So we had the A1, Y1, okay? Now we have established this. So this particular one has been simplified to this, 1 over 4D plus D. So this one has been simplified to this, okay? Now let's move to the next part. With the area 2 part, as you can see, we have established this one. We have also established this one. And this one has been simplified further to half d over 2 plus y. Okay? So these components, as I said, we have to calculate our ay bar as a1 y bar 1 plus a2 y bar 2. So with the various parts, putting them together, we'll have something like this. Okay, so the first term represents a1 y bar 1 and then a2 y bar 2. So in the next slide, what we are going to do is we are going to simplify this further to get a smaller equation. Okay? So this same equation is brought here now. This same equation. This same equation is here now. So we are to simplify it. Of course, this is basic mathematics. So trying to simplify this further, you have it like this. AY bar. In trying to simplify it to the lowest, you have it in this form. T over 8, b over t, capital D square minus small d square plus small d square minus 4ay squared. This one will give us the ay bar. Okay, so that is trying to simplify it to the lowest level. Is that okay? Now, so now that we've got our a bar, y bar, we are now going to now substitute into the mean shear formula to determine what we expect. So now, this is the main shear formula. Oh, as you can see, I'm using small w to represent the shear stress in the web. So this one is the substitution. Okay, you can see the F, you can see the T, you can see the I. And this in the square bracket here was what we just calculated, the A Y bar. Okay. This is the A Y bar. Okay. All right. And remember that because we're in the web, this B here is now small t. And further simplification of this equation down, we'll get equation 3. Once again, this one is for I section and for the web only. So if you want to deal with the web, this is the formula. When you check it, you realize that everything here is simply known. The only thing not known is the y. So simply get your y values. Once you substitute into equation 3, you get your answer. Okay, so I want you to also write the equation 3 down. I want you to write that and note that that one is for the web. And then that one is for the web. Joshua.
Sir, I wanted to add up to what you said.
Okay.
If the figure is symmetrical, the top flange, the equation for the top flange will be equal to the equation for the one beneath.
Yeah,
right.
Even if it is not symmetrical, as far as it's an I section, the flange equation is the same equation you use for the top and for the bottom.
But just that the figures will be different.
Yes, there will be changes, right? So what you should remember is when we say I section, it can be in several shapes. You can have it like this. You can have this one and the bottom very big. Once it's an I section, it's valid. Is that okay?
That is okay.
Right. Okay. So I'll take you to a favorite table I created, trying to summarize all this together to make life easy for my people. So you see that I have put this together. So we have here this equation 1, which is the general equation for calculating the shear stress across the section, irrespective of the shape. But we looked at rectangular. This is also applicable to square shape. Okay? And as you can see, when we want to calculate the shear stress at any point, this is the formula. Equation 2. When it comes to the I section, if you want to calculate the shear stress in the flange, this is the formula. And you see that the only thing that will be changing here is a y. And if you want to do that for the web, this is the formula. This is beautiful. Okay, so I want to say that if we take a typical I section, okay, I think my drawing is very small. Let me clear it. Let me draw it here. If we take a typical I section, very big I section, okay, look at the points of interest. Of course, the neutral axis is somewhere here, okay? This is the neutral axis. And I believe we have learned how to find the neutral axis. That is the center of gravity. The line that passes through the center of gravity is called the neutral axis. In other words, the centroid for plane figures. So for I section, we have the flange, the top one. We also have the bottom flange. Okay? And then this is the web. So typically, you are measuring Y upward and Y downward. So if this is negative, this must be positive. So the points of interest, the topmost part of the flange, number one. And then another point of interest is here, 2. That's for the flange. And then you have to also calculate here, 3 and 4. But if it is symmetrical, note that these answers will be the same. Then when it comes to the web, points of interest, 5. Okay? And the neutral axis here, which is 6. And of course, this part is also of interest. So if you be able to draw the shear diagram, these are the critical points you have to calculate. But let me add that you can calculate several points as you want. So let's say the T is 10 millimeters, you can do it at every 1 millimeter interval. But I am only showing you critical areas that when you are able to calculate, you can plot your shear diagram. Okay? And if you talk about rectangular section, that one is even easy. You just need here, you need a neutral axis, and you need here. Just 3 calculations there. You'll be able to plot your diagram. Okay? All right. So this is aggregation of the formulas. So if you like, you can take a screenshot of this one whilst we proceed with our work. Okay. Let me proceed. So what are the basic steps to follow in this particular case? I say, well, calculate the shear force at the required section. So depend on the beam that will be given to you. If it's a standard case, usually we are looking for where maximum shear force is acting. Okay? But we can also find it at where any point within the beam, we can find it. Okay, any point within the beam. So note that if this is the beam, we have support here, we have support here. If this is the section we are considering, we are calculating the shear stress here. If we are calculating it here, you find the shear force at this section and use it for the calculation. But in the case where it is not mentioned, you are now looking for maximum shear force in the member. Because of course, the maximum will give you the extreme value. So the critical point to look for is where we have the maximum shear force. That's where your interest will be. All right. Calculate moment of inertia of the section. This one too, we have dealt with it. And then calculate the distance of the fiber to the neutral axis. That is from the point of interest along the depth of the beam. If you remember, this is the Y. And use the general shear formula or the simplified formulas to determine the shear stress. Okay, so we have done for only rectangular and I section. There are several kinds of section. We have T section. So T section, the same approach, you can use it to generate formulas. Okay, you can use any section at all. The same procedure we use can be used to generate these formulas for all of them. And even these formulas as we have given, you can put them into Excel. Said that once you put in your Y values, it gets the calculation for you automatically. And maybe this may be part of the coursework in subsequent classes. But if this class is ready to take another coursework, I can give it. You know. So I feel that this class is ready for another coursework. So So that's what I've been told. So maybe I'm going to give it as a coursework. But if you say you are okay there, why not? I go left hand. Then use the plot the shear stress distribution diagram. So these are the basic steps we have to follow. So let's see some work examples. Okay, this is a work example. A simply supported beam of rectangular cross section, 160 mm wide and 300 mm deep, is of 4-meter span and is loaded with a central point load of 50 kN. Determine the shear stress at the top and bottom, 50 mm and 100 mm from the top and bottom. And at the neutral axis, employ the shear stress distribution diagram. Okay. So the important point now is we have been given rectangular cross section. This is 300. And they say we should determine at the top and bottom. That's number one. We are to determine 50. So from here, 50. And then from here to 50. And then we are to determine from here 100. From here 100. And as far as everybody should know that y is calculated from the neutral axis. Y, right? Y is calculated from the neutral axis. So y either this way or that way. If we take this to be a positive, this should be the negative, and vice versa. Okay. So if you look at it carefully, for the top at the 50, as you can see here, and y will be equal to what? This is the d. This is overall d. So d over 2 is what? 50. 300 over 2, which is what? 150. So if we want at the top extreme, then the y will be equal to what? 150. If we want at this point, the 50 from the top, then it means it's the 150 minus the 50, which will give us this distance. And similar calculations will be done. Okay, so let's look at, we have been given the shear force, the load. We have been given a configuration of a beam. And this is the data extracted. Okay? This is the data extracted. And what you should remember is that once we have not been told a particular section, we have to calculate for maximum shear force. And if you remember, a beam of this is a standard beam, right? So either you use first principle to do your calculation, or use the formula because this is a standard case. So use the formula of shear max, maximum shear force to be equal to P over 2. And I believe you remember these formulas, all right? Okay. So what I'll do is that I'll first try and calculate my y values. Okay, solution. So this is the formula once again. And because of this one, you can still use this one, but using this one becomes easy. So we will use this formula. And remember, because the rectangular section, we are applying this formula. Now for rectangular sections, I is what BD cube over 12. And when you calculate this, you should get 360 10 to the power 6 mm. Maximum shear force for the beam we have been given is P over 2. And this is 25 kN. And as you remember, we calculate in small units. in small unit. Okay. So I hope you have tried to see whether you get the answer for the I and co. So what is left here? What is left here is the calculation of our y. So we have to go and calculate y for each of the points we have interest in. And that brings about this table. Sometimes I try to work in tabular format to make life easy. Okay. You can adopt any way, but well, I think that this is okay for me. I think there's here is 50, not 150. Okay, so like I explained earlier, from the top, neutral axis. From here to here is d over 2. And we say 50 from the top. So this is the 50. So the actual y is from here to here. And it's the d over 2 minus the 50. Okay. Hey, sorry, at the top is the d over 2. Okay, d over 2, that's 150. And then 50 millimeters from the top. It is not from neutral axis. So from the top, so it means when we measure from the neutral axis to the 50, it's simply d over 2 minus the 50. And this gives us 100. Similarly, 100 from the top is d over 2 minus 100. This will give us 50. Neutral axis, y is 0. And then from the bottom, we are using negative to measure our y. I mean, as we explained earlier. So this one will give us negative 50. This is negative 100, and this is negative 150. And negative 150 is all the way from here all the way to here, the negative 150. Okay. Any question? So what are we going to do? We are going to substitute this into the formula. So in order to know, let's deal with the first one. Top of the section, y is equal to 150. Okay. So substitute y is equal to 150 into this equation. Y is equal to 150 mm. Put it into this equation and calculate and tell me what you get. Calculate it and tell me the answer in the message box. Any answers? No, Joshua, what's the problem?
Please, I want to know the value for the d square.
But what's the value of the D we have been using?
Unless I go back to the question, because it's like I don't me.
Can you see it?
Oh, okay. I've seen it.
Any answers so far? Hey, Joshua, how come you got negative 1.111? There's a problem. You have to check your comment. So, who is user? Please name yourself. Oh, that's your name, user. Your answer is correct. Okay, so I'm not getting answers, so let's proceed. Okay, Richard, they do. You also got it right. Okay. All right. So I've seen Jonas has also got it right. So let me just quickly go and show that slide. This is not any difficult. So based on the values, okay, I can see Ima, Alfred, Nayan, and Co. You have got it right. These are the values you have calculated. So at the top, we just substitute the values and generate these figures. So at the top, the Y is 150. This is 100. This is 50. This is 0. So you substitute this into the formula and calculate. Okay? So these are the values, as you can see. Then it continues up to this point where I finally done the calculation. So once you finish your calculation, the next step is to go and plot your diagram. Okay? Once you finish your calculation, you plot your diagram. So you see that we have 0.434, 0.694, 0.781, 0.694, 0.434, and co. Okay. So now this is how the diagram should look like. So this diagram, this is how you plot it. So the blue line, as you see, they are the various points we are calculating the bending stress. So I will draw a straight line here to represent the depth of the beam. At the top, I had 0. The next point, okay, I had 0.434. Then I plot. From here, I'll measure 0.694. From here, I'll measure 0.781. From here, I'll measure this. From here, I'll measure this. And here was 0. So you connect these lines together with a smooth curve. Note that this is a graph, but you need to use graph sheet, but just use approximate drawing, just like we did for the bending moment, and it's enough. Okay? And that should be enough. So essentially, this is how your shear diagram should look like. And this diagram, as the shape will not change. For a typical rectangular section, this is how the shape look like. Parabola. The shape is parabolic. Okay? So these points were 0. Okay? Any question? Any question? So let's try now and solve one more example, and then we'll bring the class to an end. Okay, so let's look at another problem here. Draw the shear stress variation diagram for the I section shown in the figure below if it is subject to a shear force of 100 kilonewton. So you see that this one there, they've given us the shear force, so there's no need to go and recalculate it. They've already given us shear force. So this is the data. And as you remember, I told you the various parts of the I section. So you see the capital D, capital B, small t, capital T, small d, and so forth. Okay. So this one, you need to get these properties right so that you will not get your calculations wrong. So then we proceed with the computation. So what do you need? You have to calculate moment of inertia. And you can either use, because it's symmetrical I section, you can use the simple approach or the power axis theory method to determine your I. And so the simple approach, as we have done in the previous lecture, that is what has been used to determine the moment of inertia. So the I is giving us 182.6467 10 to the power 6 mm4. You can use this one. That's the alternative approach. Power axis theory. Use this one. Okay, so let's note the value of the I that has been calculated. Okay. So we proceed with the solution. So now with the shear distribution in the flange, if you remember our formula, this was the formula. And we say that in the flange, in the flange, at the top edge of the flange, y is equal to d over 2. Okay? This is the neutral axis. So from here to here, this is the y we are talking about. And this is equal to d over 2. So you calculate that, and then you substitute into the equation. So wherever is y, you put 200, and this gave a 0 result. At the bottom of top flange, this top flange. So at the bottom here, what do you think is the y? This y here is equal to a d over 2 minus 2t. This formula is not right. This formula is not right. It should have been d minus 2t over 2. The y should be equal to d minus 2t over 2, or d over 2 minus t. Okay. So it should have been d over 2 minus t. So it means that there's problem, isn't it? So let me see. What is the overall depth was 400. 400 divided by 2 is 200 minus 10. Okay, so the answer there, this answer is not correct. This should have been 190. Okay. So this answer is not correct. So the substitution here is right. The 190 is the correct answer. So you do your substitution. Can we cross-check this one? Can we cross-check this one, whether you get 1.07? Please kindly cross-check it, whether you get 1.07. Kindly cross-check whether you get 1.07. Even if one person should be able to get the answer, it's enough. Cross-check. So these two should not be there. So this formula, the y here should be equal to d over 2 minus t, which is equal to 400 over 2 minus 10. 190 millimeters. Has anybody got the answer at all? Okay. So no problem. I'll proceed. Okay, so Victor has been able to get, so it means that, yeah, it's right. Okay, Alfred too has also confirmed. All right, so thank you for confirming. So that is that. Then we continue. So this one is for the top flange, okay? And then this one is we look at the web. The web. For the web, we remember this was the formula. Okay? I think nobody should be worried about these formulas. my principle is that if remembering long formulas is not part of an examination, and so these long formulas, if there will be any question of a sort, I'll provide these formulas. Okay? So nobody should be worried about these formulas. I think that trying to remember long formulas and write before using it for calculation, I think I'm making it a thing of the past. So if I'm going to require you to do such calculations, I'll provide these long formulas for you. So tau web is equal to this. And shear stress at the junction. So if you are dealing with a web, so like I said earlier, if we are doing the web, we deal with this part. And also at the neutral axis. So that's for the web. So for the web, and this part is simply d over 2. Okay, that will be 380 over 2. And that is 190. So you substitute 190 into this equation with all the other parameters, as you can see here. And then you generate this answer. Shear stress at the neutral axis, y is 0, right? Y is 0. So put 0 into this equation and generate this value. So you can note that we have calculated from the top. So a similar calculation have to be done for the bottom by using the appropriate values. And of course, because this is symmetrical section, the values we use here, they will be the same. Okay? They will be the same. Okay, so the formula for the top, the flange, is valid for both top flange and bottom flange. And the formula for whatever, they are all valid. Okay. All right. So all the calculation we have done so far is whatever above the neutral axis. So I was mentioning, because this is symmetrical section, when you calculate for the bottom, you get the same values. So no need to worry about it. Okay. So let's go back quickly here. When we look at the flange, we have 0 and 1.07. And then when we look at the web, we had 19.22 and 29.1. Okay. So what you do is this. So you are going to draw a single line like this to represent the depth of the overall beam. Yeah. This one goes. So these are the projections you do. This one also goes. This one goes through the middle like this. Okay. So what you do is that at the top, when you calculated, you got 0 for the flange. And then for the flange at the bottom, you had 1.06. So you do this. And then for the web, you had 19.217. And then at the neutral axis for the web, you had this value. So it's like from here, this is the line. So you always measure from here to hit this. So from here to here, you plot. So from here all the way to here, you plot this one, which is the same as 19.217. And then the web, the bottom flange is also the same as the top flange. You plot and plot. So when you finish, this small part here is a curve, a smooth curve. This is horizontal line. This is a smooth curve. Okay. this horizontal, this is also smooth curve. And at the end of the day, you will get the figure we have here. And that's typically how you do your computation. Is that okay? So if you take a classical case of unsymmetrical section, like this one, know that this will be your center neutral axis. So you have to deal with, maybe you consider this to be positive and from here down to be negative. So please deal with this one, the flange here, using the same formula. Okay, but you have to calculate this your values separately, because this is unsymmetrical, it will not be the same. So you have to calculate this value and calculate from here also and substitute all of them. So the value you get here should be negative. This will also be negative, and then substitute into the equation and generate your formula, your answers. And you do same for the web. The neutral axis will be same, but you need to substitute here into the formula and also here. And when you finish, these values you are going to get, you use them to plot your diagram. Any question? And so as you can see, for symmetrical eye section, these are the shape looks like. And like I said earlier, maximum shear stress occurs at the neutral axis. Okay? Maximum shear stress occurs at the neutral axis. All right. Any question? Now, I have some trial questions for you. And you can take a snapshot. In fact, I have uploaded this slide already on the LMS. And so it's available. So you are going to deal with this section. Okay. And then, so you have to know that you have to calculate your center of gravity first. And the line along the center of gravity is your neutral axis. So you deal with this one. And there's another one too here. Try and do that also. Try and do this one also. And at the end of the day, you draw your shear stress variation diagrams. And this brings us to the end of lecture 10. Okay. Let us note that subsequent lecture will be torsion. So please start reading something around torsion. Okay. Start reading something around torsion. That will be lecture 11. Start reading something around torsion. Okay. So any question? If there's no question, okay, Joshua. Yes, Joshua.
I want to ask, it always begins at 0 into 0.
What?
Yeah, shear force diagram.
Not necessarily,
I'm
but we
talking about
say
the
at
shear
the
force diagram.
extreme,
I'm asking what
shear force or shear stress.
shear stress, sorry.
So the principle is that at the topmost and bottommost fibers, the shear stress is 0. That's the principle you should know. And of course, your formula should give you the answers, right? So these are not arbitrary. When you substitute, you should get the answers from your formula to draw your diagram. Right?
Okay, sir.
I want to entreat all of you to do further work, try to learn, try to do some more examples, and I believe that everything will be fine. Okay? I want to thank you for your attention and thank you for being part of the class. If let me just pray shortly. But if you have any comment on today's class, I'll give you opportunity to share your comment. Do you have any comment? Any comment? Okay. All right. So we end today's class in the name of God, the Father, of the Son, and of the Holy Spirit. Thank you. And have a great day.